Divisibility is one of the central pillars of number theory. A number evenly divides into another if the first number is a factor of the second. In fact, our work on factorization and the primes from our sojourn into analytic number theory implicitly underscored the important idea of divisibility. If a number does not evenly divide into another, then there is a non-zero remainder resulting from that division. Here we'll study these remainders and discover a new and delicate arithmetic known as modular arithmetic. We'll begin by revisiting the long division we all learned in elementary school and its sophisticated number theory counterpart known as the division algorithm. By repeated applications of the division algorithm, we come upon a method for finding the greatest common factor any two natural numbers share. This important process is known as the Euclidean algorithm. As we'll introduce the main ideas behind modular arithmetic, we'll make the realization that this type of arithmetic simply captures the mathematics of cycles, such as hours in the day, in which we return to the exact same time every 24 hours, or days in the week, in which we return to the same day every 7 days. In fact, many individuals refer to modular arithmetic as clock arithmetic. The study of the arithmetic of remainders is important from a mathematical standpoint and also from a practical one. As an illustration, we'll consider the sequence of numbers at the bottom of every bank check, called the bank routing number. We'll discover that hidden within those digits of debt is a number theoretic coding scheme that reduces the chance of an error in reading the data. This error-checking code actually involves the modular arithmetic of remainders. Thus, we'll realize that every time a check is processed, a number theoretic calculation involving modular arithmetic is taking place right within our checking accounts. Similar error-checking schemes underlie the zebra-striped barcodes known as universal product codes, or UPCs, that are tattooed on nearly all merchandise today. Well, up to this point in our course, to understand the personality of a natural number n, we've studied the prime numbers that evenly divide into n. In order to identify more subtle personality traits of a natural number, we now turn to the more general idea of division. Long ago, we learned a method for dividing one number into another called long division. If we divide 47 by 3, we first notice that 3 goes into 4 once, 1 times 3 is 3, and 4 minus 3 is 1. We have that number 7, so we bring down the 7, and we see that 3 goes into 17 5 times. 5 times 3 is 15, and when we subtract 15 from 17, we see 2. 2 is actually smaller than 3, so the process stops, and thus we conclude that 47 divided by 3 equals 15 with a remainder of 2. Now, the number 15 is called the quotient. Well, suppose now that we're asked to divide 51 by 4. Before we even embark upon this division challenge, we wonder what are the possible values for the remainder. Well, in this example, because we're dividing by 4, the possible remainders are 0, 1, 2, and 3. Those are the only possible remainders. Well, 4 goes into 51 12 times, and we're left with a remainder of 3. And in fact, we could check that 51 actually equals 4 times 12 plus 3, or 48 plus 3, which is 51. If we divide a number a by a number b, then the remainder will be a number from the list 0, 1, 2, 3 out to b minus 1. The remainder actually will equal 0 precisely when b divides evenly into a. In other words, when b is a factor of a. The formalization of long division is actually called the division algorithm, and it states that for natural numbers a and b, if we divide a by b, then there exists a unique quotient q and remainder r satisfying that a equals b times q plus r, with the additional condition that the r is between 0 and b. And the r can actually equal 0, but it has to be strictly smaller than b. So in our previous examples, we would write 47 equals 3 times 15 plus 2. Notice that plus 2, that's the remainder part. And as we saw already, 51 equals 4 times 12 plus 3. Again, that small number 3 represents the remainder. Thus, since we see in both of these cases non-zero remainders, without any further work, we conclude that 3 is not a factor of 47 and 4 is not a factor of 51. Well, we now move from the study of the arithmetic personality of a single natural number through factorization into primes to seeing similarities between the arithmetical personalities of two natural numbers. Given two natural numbers, we wish to find the largest number that is a common factor of the two given numbers. For example, if both numbers are even, then they would both share the common factor of 2, but perhaps they still have more factors in common. The largest number that is a common factor to both a and b is called the greatest common factor of a and b. This number is also known as the greatest common divisor of a and b. If the two given numbers are small, we can easily find their greatest common factor by just factoring each number into primes and picking out all the common factors. For example, if we wish to find the greatest common factor of 30 and 42, we can just factor each. 30 equals 2 times 3 times 5, and 42 equals 2 times 3 times 7. And then we just multiply all the common factors. Notice they both share the factor 2, they both share the factor 3, so we multiply 2 times 3 and get 6. And thus 6 is the greatest common factor of 30 and 42. Well, this divide and conquer method will always work in theory. But in practice, if we have two huge numbers, it's not very practical. So, suppose, for example, we wanted to find the greatest common factor of 217 and 245 without a calculator. Not so easy to factor those big numbers quickly, at least not for me. Well, as we've seen, to find the greatest common factor, we can factor each number and multiply the common factors together. However, if the numbers are large, finding the factors might be very difficult. So the question remains, is there a practical way to find the greatest common factor of two numbers? Well, the answer is yes. And the way we do this is by realizing we have a challenging task. And so instead of performing the challenging task, we convert the challenging task to a long list of very easy tasks. A great life lesson that we learn from number theory, that when faced with a hard, difficult, challenging issue, perhaps it can be broken down into many, many, many pieces, each of which is simple. Well, in his Elements of Geometry, Euclid describes an algorithm for finding the greatest common factor of two numbers. This process is perhaps the oldest algorithm ever devised. This procedure is now known as the Euclidean algorithm. Now, the algorithm is based on an important fact, and I want to share the important fact with you right now. Whenever we're given the equation that A equals B times Q plus R, then the greatest common factor of the A and the B is actually identical to the greatest common factor of the B and the R. So the greatest common factor of the A and the B is the same as the greatest common factor of the B and the R. And just using this fact, we can repeatedly apply the division algorithm to a divide and conquer method in order to work our way to the greatest common factor of two numbers. Well, to illustrate the method, we apply the Euclidean algorithm to find the greatest common factor of 30 and 42. Now, we've already done that, but I want to introduce the method with an example that we've already seen. Well, we begin by dividing 30 into 42. It goes in once with a remainder of 12. In other words, we see that 42 equals 30 times 1 plus 12. So, from the principle I just outlined, the greatest common factor of 42 and 30 must be the same for the pair 30 and 12. And notice that 30-12 is actually a smaller pair than the original 42-30. So again, we've reduced things a little bit, just a little bit though. This is the divide and conquer approach. Well, therefore, we now divide 12 into 30. It goes in 2 times with a remainder of 6. In other words, 30 equals 12 times 2 plus 6. Again, we have that the greatest common factor of 30 and 12 must be the same as the greatest common factor of 12 and 6. Well, now we can see that the greatest common factor of 12 and 6 equals 6. And we can actually see this because 6 is a factor of 12. In other words, 12 equals 6 times 2 plus a remainder of 0. Well, when this repeated division process generates a remainder of 0, then the previous remainder, in this case 6, is in fact the greatest common factor of the original two numbers. This process is actually the Euclidean algorithm. Now, if we apply the Euclidean algorithm to find the greatest common factor of 217 and 245, then we just repeat the division process we just outlined. And so now we're going to take a look at how this difficult problem can be broken down into a succession of easy little simple problems. We divide 217 into 245 and obtain 245 equals 217 times 1 plus a remainder of 28. So we now divide the 28 into 217. And now we obtain that 217 equals 28 times 7 plus a remainder of 21. Well, we now divide 21 into 28 and obtain 28 equals 21 times 1 plus 7, remainder 7. And now we divide 7 into 21, and this is actually going to be easy to see, that 21 equals 7 times 3 plus 0. Now, we get to 0. So once we find a remainder of 0, we return to the previous non-zero remainder, and that equals the greatest common factor. Thus, we see that the greatest common factor of 217 and 245 is actually 7. Now, we could actually check and see if our answer is correct by actually factoring those numbers, which is a little tricky, but I've worked this out. 217 is 7 times 31. And 245 equals 5 times 7 times 7. And notice the only factor they have in common is in fact 7. And so therefore, we see that 7 is indeed the greatest common factor of those two numbers. But notice that we found the greatest common factor not by factoring, which is hard, but by just a succession of long divisions, which actually is doable. And in fact, in most cases, pretty straightforward and easy. Recall that a natural number greater than 1 is prime if it has no factors other than 1 and itself. Now, we'll extend this notion to pairs of numbers. We say that two natural numbers, a and b, are relatively prime if they have no prime factors in common. In other words, if their greatest common factor is the number 1. For example, 6 and 49 are relatively prime. Notice that 6 equals 2 times 3, and 49 is simply 7 times 7, and they have no factors in common other than just 1. On the other hand, 12 and 20 are not relatively prime because they actually share the common factor of 4. Well, if we use the Euclidean algorithm with a and b, then those two numbers are relatively prime precisely when the last non-zero remainder that we see equals 1. For example, if we return to the pair 6 and 49, then we see that 49 equals 6 times 8 plus 1. And that plus 1 tells us that, in fact, those numbers are relatively prime. Now, here's a neat little fact that I want to share with you. If we backward solve for the remainder of 1, then in this case, we'd find that 49 minus 6 times 8 equals 1. In other words, we see that we can find natural numbers, let me call them x and y, that actually are solutions to a certain equation. And the equation in this case would be 49x minus 6y equals 1. And in this case, we see that the solution would be x equals the natural number 1 and y equals the natural number 8. And if we plug them in, we just saw from using the Euclidean algorithm, the one-step Euclidean algorithm, that we have a solution to this funny-looking equation. Well, in fact, more generally, if two given numbers, let me call them a and b, are relatively prime, then we can always find natural numbers, x and y, that are solutions to the equation a times x minus b times y equals the number 1. Now, this little fact will be extremely useful in our discussion of public key cryptography in Lecture 12. So I wanted to mention it and highlight it here because we'll return to this very important fact about two numbers that are indeed relatively prime. Well, given two natural numbers, if the division algorithm yields a remainder of 0, then we know that the smaller number divides evenly into the larger. If the remainder is 1, then we just saw that those two numbers are relatively prime. We learned something about how the two numbers interact with each other. Well, we now focus on the remainders themselves and see, after we divide, what we get. As an illustration, let's consider just the remainders when the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth are divided by 4. So let's take a look at the entire list of natural numbers, including 0 now, and divide by 4, and just look at the remainders. Well, if we take 0 and divide it by 4, we get a remainder of 0. If we take 1 and divide it by 4, we get 0 with a remainder of 1. If we take 2 and divide it by 4, we get 0 with a remainder of 2. If we take 3 and divide it by 4, we see 0 with a remainder of 3. If we take 4 and divide it by 4, we get 1 with a remainder of 0. And if we take 5 and divide it by 4, we get 1 with the remainder of 1. And notice what happens. We seem to be cycling. The remainders are 0, 1, 2, 3, 0, 1, 2, 3. And the process and the pattern actually continues. So we observe that the remainders cycle through the numbers 0, 1, 2, 3, like a clock with 4 markings on it. For example, the remainders would look like this. We have 0, 1, 2, 3, and what we're seeing is we have a remainder of 1, then a remainder of 2, then a remainder of 3, and then we come back to a remainder of 0 again. And then we have 1, 2, 3, and so forth. So in fact, we could actually consider this clock that actually has these numbers on it, and we can work from there. Now, we cycle around and around, and notice that once we actually arrive at 3, then the next number we see is actually back to 0, just like a clock. And so this is actually similar to the arithmetic that is used to tell time, not only in terms of seconds and minutes and hours, but also in days of the week, months of the year, and so forth. So, for example, on a 12-hour clock, 14 o'clock is really 14 minus 12, which is 2 o'clock. We cycle around once, and we pass through that 12 marking. Well, this type of arithmetic, the arithmetic of remainders, is known as modular arithmetic. Modular arithmetic corresponds to the arithmetic of cycles that we use for time, as we just saw. So, for example, suppose we consider division by 4 again. Well, if a number having a remainder of 1 is added to a number having a remainder of 1, then the sum will have what remainder? Well, let's take a look and see. So here's our clock. Suppose that we have a remainder of 1, and then we add 1. Well, if we add one more remainder, we see that, in fact, the remainder would be 2. So, for example, let's take a look at 5 plus 9, which equals 14. And look at the remainder when 14 is divided by 4, and we see that it's 2. And notice that the remainder when 5 is divided by 4 is 1, and the remainder when 9 is divided by 4 is 1. And so we're seeing 1 plus 1 equals 2, and the clock shows that. Now, if we again consider division by 4, then when a number having a remainder, let's say, of 2 is added to a number having a remainder of 3, let's see what we get. So we start off with a remainder of 2, so here we are, and now we're going to add 3, a remainder of 3. So I add 1, 2, 3. The remainder should be 1. So we can see that on this clock, but we can actually look at an example. For example, let's just notice that 6 plus 11 equals 17. Now, when we divide these numbers by 4, what do we see? We see that 6 has a remainder of 2, and 11 had a remainder of 3, while 17 has a remainder of 1. And so we do see that 2 plus 3 equals 1 when we just look at the remainders. So we need only focus on the cycle of remainders, and we no longer need to focus on the quotients themselves if all we're after is the study of remainders. Thus, we're always working with numbers that are relatively small compared to the divisor, because they're always between 0 and 1 less than the divisor. We refer to this arithmetic of remainders when dividing by 4 as arithmetic modulo 4, or abbreviated mod 4. That means that all we're looking at is the remainders when we divide by 4, modulo 4. So the clock has 4 entries from 0 to 3, and then we spin around. So given our previous example, we would say, and we're going to introduce, let me introduce some notation here. What we do is we don't say that 6 plus 11 equals 1, but we use this idea of equivalent. And we use, instead of the usual equal sign that has like 2 little horizontal lines, we use 3. We up it, which means that they're not identical, but they have the same remainder. And we read the 3 equal signs as either equivalent or congruent. So we would say that 6 plus 11 is congruent to 1 mod 4. So what it means is that the remainder of 6 plus 11 is actually going to equal 1 when we consider division by 4. Well, because 5 plus 9 equals 14, and 14 has a remainder of 2 when divided by 4, then we could write, using this notation, 5 plus 9 is congruent to 2 mod 4. Well, although people have been studying remainders since at least the 3rd century, when the Chinese were proving interesting theorems involving the cycles of remainders, modular arithmetic was formally introduced by Gauss in 1801. Modular arithmetic is a powerful tool that allows us to establish subtle divisibility results through the use of basic arithmetic, and that's the power. We can use basic tools to say something about subtle issues. For example, if the difference between 2 numbers is congruent to 0 mod m, then that tells us that those 2 numbers will have the same remainders when each is divided by m without the need to actually perform the long division. So as an illustration, we again consider arithmetic mod 4. Again, remainders when we divide by 4. Now notice that 103 minus 95 equals 8. And when you divide by 4, the remainder when you divide by 4 of 8 is going to be 0. So 8 is congruent to 0 mod 4. So we see that 103 minus 95 is congruent to 0 mod 4. So we conclude that 103 has the same remainder as 95 when divided by 4. And we deduce this fact without ever performing long divisions. You can see the power of this analysis. And in fact, we can check this in case you have doubts. Using the division algorithm, we see that 103 is actually 4 times 25 plus 3. That's pretty easy. And 95 is actually 4 times 23 plus 3. And we then confirm that indeed these 2 numbers do have the same remainders. Both remainders are in fact equal to 3. Well, to illustrate the power of modular arithmetic, I want to consider a real-world example. While modular arithmetic plays a central role in mathematics in general and in number theory in particular, here we offer some illustrations of how modular arithmetic is used in our everyday lives. Now, the bank routing number is a 9-digit number located on the lower left corner of any check. And in fact, you might want to get out your checkbooks and follow along. It actually identifies the bank from which the check is issued. So each bank will have a different routing number. Now, computers scan the routing number along with the bank account number that appears to the right of the routing number and electronically make appropriate withdrawals. Well, to prevent errors in reading these numbers, encoded in the routing numbers is a check that involves modular arithmetic. Now, to check a bank routing number, we take the 9 digits that we see, and I'm going to give them names now. Let me call them A, B, C, D, E, F, G, H, I. Each of those represents one of the digits in this 9-digit bank routing number. And we produce the following very strange combination of these digits. We're going to take the first 3, A, B, C. We'll multiply the first number A by 7, the next number B by 3, and that last number C by 9. And then we're going to look at the next 3 numbers, D, E, F, and do the same thing. Multiply the first by 7, the next by 3, the last by 9. And then with the last 3 digits, G, H, I, we repeat 7, 3, and 9. So what we get is, and then we take all those numbers, by the way, and I want to add them all together. So here's the strange number we concoct. 7a plus 3b plus 9c plus 7d plus 3e plus 9f plus 7g plus 3h plus 9i. Now, a little, peculiar looking, but you have to admit it's just a number and pretty easy to figure out. We now consider this auxiliary number modulo 10. That is, we consider its remainder when divided by 10. The bank routing number is designed so that this remainder equals 0. So if the remainder is not 0, we know we have an error in reading the number. Well, divisibility by 10 is very easy to check. A number is evenly divisible by 10, so it has remainder 0, precisely when the number ends in a 0. For example, one branch of Citizens Bank has routing number 036076150. If we produce the corresponding auxiliary number, we'd see 7 times 0 plus 3 times 3 plus 9 times 6 plus 7 times 0 plus 3 times 7 plus 9 times 6 plus 7 times 1 plus 3 times 5 plus 9 times 0. And that works out to be 160. I worked that out in advance, actually. I didn't do that in my head. Well, 160, notice, has a remainder of 0 when divided by 10, because the last digit is a 0. Notice that I'd write this as 160 is congruent to 0 mod 10, which is consistent with a valid routing number. Well, we can use this code to determine a missing digit in a bank routing number. So, for example, suppose we were able to only partially read a Williamstown Savings Bank routing number. Specifically, suppose that we knew only the first few numbers. In particular, let's say that we read 211-872-94, and that last digit was somehow not read. So that last digit's blocked from sight. Well, we can compute the auxiliary number for this bank number as best as we can. 7 times 2 plus 3 times 1 plus 9 times 1 plus 7 times 8 plus 3 times 7 plus 9 times 2 plus 7 times 9 plus 3 times 4 plus 9 times unknown, so 9 times question mark, which simplifies down, if you do all the addition that you can, to 196 plus 9 times the unknown digit. Well, we know that this number must have a 0 remainder when divided by 10. And to have a remainder of 0, mod 10, we must find a multiple of 9. That mystery number, when multiplied by 9, has to end in a 4. So that digit 4, when added to the last digit of the other number, 6, will produce a number that ends in 0. So we need to think to ourselves and determine what digit, when multiplied by 9, will end in a 4. Well, the answer is 6, because 9 times 6 is 54. So if we let our mysterious digit equal 6, then our auxiliary number becomes 196 plus 54, which equals 250, which indeed has a remainder of 0 when divided by 10. Thus, we'd actually figured out the last digit of this bank code. It ends in a 6, and we did that using modular arithmetic. In fact, you can try this at parties if you want. Have someone rip out a check and cover up one of the digits. You have to memorize that special way of producing the auxiliary number, but then if you can do the arithmetic in your head, or even not, in fact, you can then tell what the missing digit is, and hopefully they'll let you keep the check. Well, this error detection method is guaranteed to detect most common errors in reading bank routing numbers, including interchanged digits and a single digit read incorrectly. Similar coding schemes using modular arithmetic and remainders are used to check universal product codes, UPC, and ISBN numbers on books, and even certain driver's licenses in certain states. We employ modular arithmetic, the mathematics of cycles, every day, both consciously when we make appointments or read a clock, but also unconsciously, behind the scenes in our technological world. Number theory allows us to see and understand many of these invisible instances with great clarity.